So what kind of wave is this? A wave in a sea? Transverse or longitudinal? So it's a transverse. As you can see, the water particles are moving up and down, and the energy actually transfer from one place to another. Now, what is frequency? The term frequency means number of vibration in 1 second. How many times the vibration occur in 1 second? We call that as frequency. So in this figure, you can see this is a 10-second timer. Like in 10 seconds, it will be about like how many vibration will be there in 10 seconds. And we can use that to calculate a frequency, because just divided by the time interval. So we'll know what will be the frequency. Now for the first one, I want you to focus on one point, and what will be the frequency as the timer start. I'll start the timer, 10-second timer. You will see the particle will start to vibrate up and down. So I want you to work out the frequency. So focus on any one point, and one vibration means, what is the meaning of one vibration? When this point will go up, then it will come down and then return back to the same place. That's called one vibration. So I want you to count how many vibrations are there for this wave in a 10-second timer. So focus on one point only. It's up to you. Any point you can take. For example, point A, I'm focusing on point A, and you can also focus on any point, because the vibration is same for all the points. How many vibrations are there in 1 second? In 1 second, how many times it will go up and down? That's called frequency. So I'll start the timer now, and you will count how many times it vibrated. Yes, how many times you find it was vibrating in 1 second? What was the number of vibration for these? And this is transverse. You can see the particles are moving up and down. Let's try again. Let's try again. I will mention, because the answer, some student got the right answer, but few of them, not all. Count the number of vibration, like how many times it is going up and down. I'll say start, so it will start. I'll start the timer now. You will count number of vibration. Start now. So how many times you find that it was vibrating? Yeah, actually, it is 10 times. The correct answer, when you count it correctly, you will find 10. See, 1, 2, 3, 4, and so on till the timer is at 10-second mark. So it is vibrating. What is the frequency? Frequency means number of vibration in 1 second. So as you can see, it was vibrating. Yeah, reciprocal 1 per second. That's correct. So it was having 10 vibrations in 10 seconds. It was having 10 vibrations. So in 1 second, how many vibrations will be there? It will have X vibration. I'll just cross multiply what I will get. I'll get 1 vibration per second. And this vibration per second or reciprocal of a second is also known as hertz. So unit of the standard unit of frequency is hertz, denoted by Hz. So 1 vibration per second or 1 wave per second you can also mention. So it is actually 1 hertz. Now another example. So frequency of this one is 1 hertz. I want you to focus on this wave as well. I'll start the timer and count how many times it vibrated in 1 second. I'll start the timer now. How many times it vibrated in 1 second? Okay, I will start again. Is it my sound is clear to everyone, or is the sound is also lagging? Okay, I will start again. You will count how many vibrations occur. Okay, count now the number of vibration in 1 second. Yeah, what it appear? How many vibrations it appear? And what do you think by looking at this wave? It is high frequency or low frequency? The second wave, what it appear to be, high frequency or low frequency? It's a high frequency because it shows like more vibrations per second. So if the number of vibration per second increase, it means yeah, more packing is because it can be distribution of particle, but in terms of vibration, you will see that is having a greater vibration as compared to first one. So it's having high frequency. And what is the frequency? So it is 1.4. So actually it was 14 vibrations in 10 seconds. That's why the frequency was. So the correct answer was 14. The 14 vibrations were there in 10 seconds, but you need vibration in 1 second. So it was 1.4. Another example of calculating a frequency. These are the points I want you to focus on, the one of the particle. How to calculate hertz? Look, if you know the vibrations, number of vibration divided by the time. You will get the frequency. So how many vibrations were there in this example? You was having 14 vibration. And how much time? I took a 10-second timer. So 14 divided by 10, that's why it was equals to 1.4 hertz. Now, how many vibrations for this wave appear to be? How many vibrations in 10-second timer? So it shows 5 vibrations. So it is having 5 vibration in 10 seconds. So if we need frequency, number of vibration divided by time interval, we'll get 0.5 hertz. And it is obvious, you can see when you compare them, yeah, 0.5 hertz is the frequency. So when you compare these waves, it is obvious by looking at these vibrations, you can simply clearly identify that the vibration of this wave C is much slower as compared to the first two. So this is having a low frequency, so it should be less than 1. And here in this example, it's about 0.5 hertz. So in a transverse wave, the particle vibrate. So frequency can be in decimal, frequency can be in whole number, and different waves have different frequencies. So this is not a fixed, like a wave should have like 0.5 hertz, 1 hertz. It can be any frequency depending on how many times the vibration of the particle occur. The second type of wave is known as a longitudinal wave. Longitudinal wave, when the particle vibrate parallel to direction of the wave. Example, these are the air molecules. Example, these are the air molecules, air particles. So when you produce the sound, you disturb the air particles. So when we produce the sound, we disturb the air particles. If a person is standing at position A, he will hear the sound. How he is able to hear the sound? Because these air particles collide with another particle that will collide with. So these air particles are colliding with each other and transferring the energy from one place to another. So you can see the direction of the particle is same as the direction of the wave. So when two directions are same, we can also say they are parallel to each other. So the wave in which the particle vibrate parallel to each other, we call that as a longitudinal wave. And to remember this longitudinal wave, you can see this word parallel, it's ending at L, letter L, and the longitudinal is starting with letter L. So it's easy to remember longitudinal wave, the particle vibrate parallel to direction of the wave, and transverse, the vibration of the particle is perpendicular to direction of the wave. So example, you have say a speaker, a loudspeaker. See, this is a loudspeaker cone. So what happened, how it produces a sound? The loudspeaker cone vibrate to and fro. This is a speaker cone. As you can see, like this is a speaker. There's a membrane here, the cone. So this membrane vibrate to and fro. So when this membrane vibrate to and fro, it collide with the air particle. So as it collide with the air particle, so air particle push each other. So which direction the air particles are vibrating? They are vibrating to and fro, right and left. And which direction the energy transfer? It's from left to right. So both are parallel to each other. When the direction of the wave and the direction of the particle parallel to each other, we call that kind of a wave as a longitudinal wave. So sound wave is example of longitudinal wave. So you can see the particles actually vibrating, transferring energy, pushing each other. Is it clear? Longitudinal wave. The region where you find a particle, because when the longitudinal wave move through a medium, you can see some regions the particles are closer to each other and some places the particles are away from each other. So the region where the particles are closer to each other, that region is known as a compression. Like the particles are close to each other, and region where the particles are away from each other, that's called rarefaction. So the region particles are closer, we call compression. And the region where the particles are away from each other, we call that as a rarefaction. Which region you think is having a high pressure? Yeah, the compression, as you can see from the name, like something compressed means high pressure. So in a compression region, the particles are at high pressure. Look, the wave is a way by which energy transfer. So particles are actually, when they collide with each other, like if you see this highlighted part, spotlight is representing the energy. So what happened? The energy is carried by the particle and they're transferring. So energy travel from one place to another by these vibration of the particle. So air is a medium through which this energy is transferred. And when this energy transferred through the air, the particles of air are vibrating parallel to direction of the wave. That's why we call this as a longitudinal wave. If I sketch a graph for pressure, so you can see compression, the pressure is high, where the rarefaction, the pressure is low. So when the wave travel, when the longitudinal wave travel through a medium, so it create a region of high and low pressure known as compressions and rarefactions. The region of high pressure is compression and region of low pressure is called rarefaction. Same way, like example, this is a source of the sound. So it is producing a sound and sound is traveling in all the direction. But how sound is traveling in all the direction? So what is the vibration of the particle? You can see the direction of the particles are actually vibrating and moving in the same direction as the energy transfer. But energy is transferred in all the direction. That's why the vibration is also in all. And the direction of energy transfer and the direction of energy or the wave is same. That's why we call this as a longitudinal wave. Is it clear? The longitudinal wave. So for a longitudinal wave, we define certain terms. We define rarefaction, the region where the particles are away. These lines are representing the position of the particles. These are lines are not particle. They are representing the position of the particle. Compression, where the particles are closer, that region is called compression. And the distance between the two successive compressions, like we know this region is a compression, this is also compression. The distance between the two successive compressions, that's called wavelength. And rarefaction, the distance between the two successive rarefactions, that is also called or known as wavelength. For a longitudinal wave, the distance between the two successive compressions or two successive rarefactions is known as a wavelength. Definition of the compression you should learn. Compression is a region where the particles are closer and the pressure is high. Rarefaction is a region where the particles are further apart and the pressure is low. Then how we can relate the frequency and speed of the wave. Frequency is how many vibration in 1 second, and it is reciprocal of the time period. Like if we know the time, if I say the wave is taking 2 seconds to complete its vibration, what is the frequency? How many vibration in 1 second? So it will be reciprocal of that. Yeah, 1/2. And for speed of a wave, the distance traveled by the wave, and wave when travel through a medium, it does not accelerate. That's called speed of the wave. But it depends on the question. There are 3 ways to calculate the speed of the wave. Number 1, for example, if wave travel from one place to another, and we want to calculate the speed of the wave, so what we will do, if I say at point A, the wave is originated, produced, and it traveled to point B. So wave travel from point A to point B, and I want to find the speed of the wave when it travels from A to B. So the formula, if there is no reflection, the wave does not bounce back or does not return back to the same starting point, then the formula to calculate the speed, as the wave does not accelerate moving from one place to another, so the formula to calculate speed of a wave is distance divided by time. So if I know the distance and I know the time interval, I can divide them and I'll get the speed of the wave. This is one way of finding the speed. But if wave travel from one place to another and return back, or reflection occur, so in that case, because what happened, the wave traveled from point A to point B and then it bounced back. So if I say the distance between A and B, the distance between point A and B is D. So what is the distance traveled by the wave? If the distance between A and B is equals to D. So wave travel and return back, in that case, the wave bounce back. So the distance travel is 2D. And divided by T, T is the total time for the wave to return back. So if there's a reflection, then the formula is speed is twice the distance divided by total time interval. If there is no reflection, speed is distance divided by time. But sometime instead of giving the distance, they give you the frequency and the wavelength. So if frequency and the wavelength given, what you will use the formula speed of the wave, I'm denoting by V, is equals to frequency multiplied by wavelength. So where V is the speed, F is the frequency, and lambda is the wavelength or the length of the wave. So these are the three formulas which we use to calculate the speed of the wave when it travels from one medium to, when it travels through a medium, in one medium from one place to another. Is it clear? The three formulas depending on the question. So according to the question, you will use the formula. Okay, in this question, which row shows the nature of the light waves, sound waves, and X-rays? I will show you the first slide so you can recall the examples. These are the examples of the transverse wave. Radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. And for longitudinal, sound waves or wave in a compressed spring, these all are longitudinal waves. So the question is, which row shows the nature of light waves, sound waves, and X-rays? So what's the right answer? C is the right answer. Light waves are transverse, sound waves longitudinal, X-rays are also transverse. You have to learn these examples. Question 3. Which arrow on the graph shows amplitude? So the correct answer is B. This is the amplitude. C is actually half of the wavelength, and A is actually twice of amplitude, double amplitude, and D is the wavelength. The diagram shows a side view of a water wave as at a particular time. The diagram is full size. Like full size here means like what is the size you see? That's according to the actual one. Which statement about the wave is correct? Look, in this question, time interval is not because in this figure, I don't see how they're vibrating. As I showed you the previous example, like in this example, I know how the particles are vibrating up and down. So I am looking at the motion of the vibration of particle. But in this is stationary, like it's a still picture. The time interval is not given. at a certain particular time is mentioned, but they did not mention like this many waves in a specific time interval. So it will be difficult to measure because we don't know. We know how many vibrations, like 1, 2, 3, and 3.5 vibration. But I don't know what time, how much time it will take for this vibration. So that's why I cannot find the frequency. I can find the wavelength. I can measure a distance between the two successive crests or two successive troughs and get the answer. Is it clear? Question 9. The diagram shows 4 waves drawn to the same scale. Which statement is correct? The numbers, like numbers are not written, but the marking is there. Like you can see 1 mark, 2. You can just write your own numbers to understand the idea. Which statement is correct? So when you check amplitude of wave P is same as amplitude of R. So what's the amplitude? Amplitude of this wave is 1 and amplitude of R is also 1. That's correct. Amplitude of wave S is double. Amplitude of wave S is double compared to Q, but both have the same amplitude. This amplitude is 2. A is the right answer, but other statements are not true. I'm just discussing why. The wavelength of a Q is double as wavelength of P. What is the wavelength of Q? It's 4. And what's the wavelength of P? That's also 4. So actually both have the same wavelengths. The wavelength of S is same as Q. Wavelength of S is 2 and Q is 4, so that's not correct. Amplitude of P is same as amplitude means height. The term amplitude means height of the wave. So when you check the height of wave P, that's 1 unit. Like you can see one mark is there. When you check the height of R, that's also equal to 1 mark. So both have the same amplitudes. The height of the wave is refers to amplitude. And the horizontal distance, that refers to the wavelength. Question 10. Yes, sound waves, because sound waves, the particle vibrate parallel, so that's longitudinal. All other are transverse. Question 11. B is the right answer. Transverse radio sound waves are longitudinal. Okay, in this question, a boy threw a small stone into a pond. Waves spread out from where the stone hits the water and travel to the side of the pond. The boy noticed that 8 waves reaches in 5 seconds. What is the frequency? So frequency is number of vibration divided by time interval. So 8 vibrations in 5 seconds. How many vibration in 1 second? So it will be 8 divided by 5, which is equals to 1.6. So C is the right answer. Is it clear? So because the frequency means how many times it vibrate in 1 second. The next one, question 14. I want you to answer question 14. Five complete wavelength means 5 waves. Because the frequency is the number of vibration per second. So vibration divided by time. 5 complete wavelength means 5 wave divided by 21 by 4 equal to 0.25. A is the right answer. Question 18. How many wavelengths are there between X and Y? How many wavelengths are there between X and Y? Look, how to count the number of the wavelengths. Look, you measure the distance from crest. This is one wavelength. And this one is a horizontal distance to trough only. So if distance between the two successive crests is one wavelength, so this horizontal distance between the crest and the trough will be half wavelength. So how many wavelengths are there between X and Y? So that's equal to 1.5 wavelengths, or one whole number 1 by 2, which is also equal to 1.5. Is it clear?